Welcome, weary travellers of the digital age. Tonight, we embark on a journey back through millennia to discover something remarkable. The seeds of computer science were planted not in Silicon Valley, not in the laboratories of the 20th century, but in the marble halls and sandy shores of ancient Greece. As you settle in for this gentle exploration, perhaps with a warm cup of tea or wrapped in your favourite blanket, we'll uncover how the philosophers, mathematicians and inventors of antiquity laid the foundations for the algorithms that power your devices, the logic gates in your processors, and the very concepts that define modern computing. It's a story that spans over 2,000 years, yet feels as fresh and relevant as the latest software update on your phone. Picture, if you will, the bustling agora of Athens, where Socrates once questioned the nature of knowledge itself. Imagine the island of Samos, where Pythagoras contemplated the harmony of numbers. Envision the great library of Alexandria, where scholars organized the world's knowledge in ways that would inspire database designers millennia later. These places, these minds, these moments in time, they are where our digital story truly begins. From mechanical computers predating electricity by 2,000 years, to encryption methods that protected ancient military secrets, to the birth of algorithmic thinking itself, we'll see how the Greeks, without knowing it, were the first computer scientists. They asked the fundamental questions that still drive innovation today. How can we automate calculation? How can we organize information? How can we think about thinking itself? Tonight's journey will take us through 10 fascinating chapters, each revealing how an ancient Greek innovation became a cornerstone of modern computing. We'll explore the Antikythera mechanism, a device so sophisticated that nothing like it will be seen again for over 1,000 years. We'll sit with Aristotle as he develops the logical frameworks that would one day become the Boolean algebra at the heart of every computer chip. We'll walk through Hero's workshop in Alexandria, where the first programmable machines came to life through clever arrangements of ropes, weights, and water. But this isn't just a history lesson. It's a meditation on the timeless nature of human ingenuity. As we explore these ancient innovations, you'll begin to see patterns, connections, and echoes that resonate through time. The recursive elegance of Euclid's algorithm, still protecting your online transactions today. The systematic thinking of Eratosthenes, whose prime-finding Sieve teaches us about optimization. The abstract beauty of Plato's forms, which prefigured object-oriented programming by 2 millennia. Each story we'll share tonight is carefully chosen to illuminate not just what the Greeks discovered, but how they thought about problems, a way of thinking that defines computer science to this day. We'll see how their pursuit of truth, beauty, and order in the universe led them to create tools and techniques that would eventually give birth to the digital revolution. So dim your lights, find comfort, and let's discover together how the ancient world gave birth to our digital one. Let the gentle rhythm of history carry you through this exploration as we trace the golden thread that connects the philosophers of antiquity to the programmers of today. Close your eyes when you wish. Let your mind wander through these ancient halls of learning and allow yourself to marvel at the continuity of human curiosity and creativity. Our journey begins now in the warm Mediterranean waters off the island of Antikythera, where in 1901 sponge divers would discover a shipwreck that would change our understanding of ancient technology forever. Chapter 1. The Antikythera mechanism. the first analog computer. In the year 1901, in the crystal-clear waters between the Greek islands of Crete and Cythera, a group of sponge divers made a discovery that would fundamentally change our understanding of ancient technology. Captain Demetrios Kondos and his crew, seeking shelter from a storm, decided to explore the seafloor near the tiny island of Antikythera. What they found was a Roman shipwreck, resting silently on the ocean floor for over 2,000 years, its cargo scattered across the sandy bottom like pieces of a forgotten puzzle. Among the amphora, statues and coins lay something peculiar, a corroded lump of bronze, no bigger than a shoebox that would take decades to reveal its secrets. This unassuming artifact, now known as the Antikythera mechanism, would prove to be humanity's first analog computer, a device so sophisticated that nothing comparable would be created for another 1,000 years. As we settle into this story, imagine the workshop where this device was born, sometime around 100 BCE. Picture a Greek craftsman, perhaps on the island of Rhodes, carefully cutting bronze gears with a precision that seems impossible for the era. Each gear tooth had to be perfect, each ratio exact. The margin for error was essentially zero. This wasn't just metalwork, it was mathematics made manifest in bronze. The Antikythera mechanism was, at its heart, a cosmic calculator. Its primary purpose was to predict the positions of celestial bodies, the Sun, Moon, and the 5 planets known to the ancient Greeks: Mercury, Venus, Mars, Jupiter, and Saturn. But calling it merely an astronomical calculator understates its elegance and complexity. This device could predict solar eclipses decades in advance, track the irregular orbit of the Moon with stunning accuracy, and even account for the 4-year cycle of the Olympic Games. Let's pause for a moment to appreciate what this means in computational terms. The mechanism contained at least 37 meshing bronze gears, possibly more. Some researchers suggest up to 70 gears in the complete device. These gears implemented mathematical ratios that represented astronomical cycles. For instance, the mechanism used a gear ratio of 254:19 to track the metonic cycle, the 19-year period after which the phases of the Moon recur on the same days of the solar year. This ratio is accurate to within 1 part in 86,000, a precision that speaks to both the mathematical sophistication and the mechanical craftsmanship of its creators. The device operated on what we would now recognize as fundamental principles of analog computing. Input was provided by turning a hand crank, which represented the passage of time. This single input was then processed through the gear train, the mechanical equivalent of an algorithm, to produce multiple outputs displayed on various dials. The front face showed the zodiac and the Egyptian calendar, while the back displayed various astronomical cycles, including the metonic cycle, the Callipic cycle, and even predicted eclipses. Consider the computational elegance of this design. The mechanism performed what we would now call parallel processing, multiple calculations happening simultaneously through the mechanical interaction of the gears. It implemented modular arithmetic through the cyclic nature of gear rotations. It even included a form of error correction, a pin and slot mechanism that accounted for the elliptical orbit of the Moon, implementing what was essentially Hipparchus's lunar theory in mechanical form. The knowledge encoded in this device is staggering. Its creators understood not just the average periods of celestial motions, but their subtle variations. They knew that the Moon moves faster when it's closer to Earth, and slower when it's farther away. They understood the complex dance of eclipse cycles, where the alignment of sun, earth, and moon creates predictable patterns over centuries. All of this astronomical knowledge was translated into mechanical relationships, bronze gears becoming the physical embodiment of celestial mathematics. From a computer science perspective, the Antikythera mechanism demonstrates several fundamental concepts that would later become cornerstones of computing. First, it shows the principle of abstraction, complex astronomical phenomena reduced to mechanical rotations. Second, it embodies the concept of deterministic computation. Given an input, a date, it produces a predictable output, celestial positions. Third, it represents one of humanity's first successful attempts at automating calculation, removing the need for manual computation of complex astronomical cycles. The mechanism also hints at something profound about the nature of computation itself. It shows that computation doesn't require electricity, or silicon, or even numbers in the traditional sense. Computation is about transformation, taking input and systematically converting it to output according to defined rules. Whether those rules are implemented in bronze gears, electronic circuits, or quantum states is, in a fundamental sense, merely an implementation detail. Recent research using advanced imaging techniques has revealed inscriptions on the mechanism that serve as both user manual and theoretical framework. These texts, barely visible after 2 millennia under the sea, describe not just how to use the device but the astronomical theories it embodies. They mention astronomical periods that match Babylonian parameters, suggesting a synthesis of Greek and Babylonian astronomical knowledge. This international collaboration in ancient times mirrors our modern global scientific community, sharing knowledge across cultures to push the boundaries of understanding. The social and cultural implications of the Antikythera mechanism are equally fascinating. This wasn't a unique device. The inscriptions and historical records suggest that such mechanisms were known, if rare. Cicero writes of seeing similar devices, describing them as recent inventions of Archimedes. This suggests a tradition of mechanical computation in the ancient world that has been almost entirely lost to history. The Antikythera mechanism is likely the sole surviving example of what may have been a small but significant tradition of analog computing in antiquity. Think about the users of such a device, who needed to predict eclipses decades in advance, who required precise knowledge of planetary positions. The answer tells us something important about ancient Greek society. This was a culture that valued precise knowledge, that saw understanding the cosmos as both practically useful and philosophically important. Astrologers would have prized such a device for casting horoscopes. Astronomers would have used it to test theories. Calendar makers would have employed it to reconcile lunar and solar cycles. Perhaps even navigators used such mechanisms to determine their position at sea. As we near the end of our exploration of the Antikythera mechanism, let's reflect on what this ancient computer teaches us about the nature of technology and progress. We often think of technological advancement as linear, each generation building on the last in an unbroken chain of progress. But the Antikythera mechanism reminds us that knowledge can be lost, that civilizations can achieve remarkable heights only to have their achievements forgotten for millennia. The mechanism also challenges our assumptions about ancient capabilities. When we think of ancient Greece, we might picture philosophers in togas debating abstract concepts, not engineers creating precision gear trains. Yet the Antikythera mechanism proves that ancient Greek technology was far more advanced than commonly believed. It suggests that our ancestors were not primitive versions of ourselves, but sophisticated thinkers and makers who happened to work with different tools and materials. In the gentle light of history, the Antikythera mechanism stands as a testament to human ingenuity. It reminds us that the desire to understand and predict, to build machines that extend our cognitive abilities, is not modern but ancient. Every time a programmer writes code to calculate orbital mechanics, every time an engineer designs a gear train, every time a mathematician reduces complex phenomena to elegant equations, they're following in the footsteps of that unknown Greek craftsman who, over 2,000 years ago, captured the cosmos in bronze. As you drift off to sleep tonight, perhaps you'll dream of bronze gears turning in eternal cycles, of ancient hands carefully calibrating cosmic machinery, of knowledge preserved in metal, waiting patiently on the ocean floor to be rediscovered. The Antikythera mechanism isn't just an artifact, it's a bridge across time, connecting ancient minds to modern ones through the universal language of mathematics and mechanism. And so we close this first chapter of our journey, having seen how the Greeks created humanity's first analog computer. But this is just the beginning. In our next chapter, we'll explore how Pythagoras discovered the mathematical nature of music, laying the groundwork for digital audio processing and the mathematical understanding of harmony that would resonate through the ages. Chapter 2: Pythagoras and the Mathematics of Harmony. On the island of Samos, around 570 BCE, a child was born who would fundamentally change how humanity understands the relationship between mathematics and the physical world. Pythagoras, whose name would echo through millennia, discovered something so profound that it forms the foundation of digital audio processing, music synthesis, and our entire understanding of wave mechanics. But let's not get ahead of ourselves. Instead, let's travel back to that moment of discovery, to a blacksmith's shop where the sound of hammers on anvils would reveal the mathematical nature of harmony itself. Picture Pythagoras walking through the streets of ancient Samos, the Mediterranean sun warming the stone pathways, when he hears something remarkable. From a nearby smithy comes the sound of hammers striking metal, but these aren't random clangs. Some combinations of strikes produce pleasing harmonies, while others create discord. Curious, as all great minds are, Pythagoras enters the workshop to investigate. What he discovers there will become the foundation of acoustics, music theory, and eventually the digital representation of sound. The hammers, Pythagoras observes, differ in weight, and the weights aren't arbitrary. The hammers that produce harmonious sounds together have weights in simple mathematical ratios. A hammer weighing 12 units and one weighing 6 units, a ratio of 2 to 1, produce notes an octave apart. Hammers with weights in a 3 to 2 ratio create a perfect fifth. A 4 to 3 ratio yields a perfect fourth. Music, Pythagoras realizes with the kind of clarity that changes civilizations, is mathematics made audible. Let's pause here to appreciate the computational significance of this discovery. Pythagoras had found that sound, something we experience as continuous and analog, could be described through discrete mathematical relationships. This is the same principle that underlies digital audio today. When your computer plays music, it's performing millions of calculations per second, transforming numbers into sound waves, implementing ideas that Pythagoras first articulated 26 centuries ago. But Pythagoras didn't stop with hammers. He began experimenting with strings, creating what we now call a monochord, a single string stretched over a resonating box with a movable bridge. By placing the bridge at different positions, he could change the effective length of the vibrating string. And here, the mathematics became even clearer. Divide the string exactly in half and you get a note 1 octave higher. The frequency doubles. Divide it at the 2/3 point, creating a 3:2 ratio, and you hear a perfect fifth. Every musical interval could be expressed as a ratio of whole numbers. This discovery led Pythagoras to a radical conclusion. The entire universe operates according to mathematical principles. He called this concept the harmony of the spheres, the idea that celestial bodies move according to mathematical equations, creating kind of cosmic music inaudible to human ears, but fundamental to the structure of reality. While this might sound mystical to modern ears, consider that we now describe planetary orbits with mathematical equations, that we understand light and sound as waves with mathematical properties, that the very atoms making up our universe vibrate at specific frequencies. From a computer science perspective, Pythagoras' work on harmony represents one of the first successful attempts at mathematical modelling of natural phenomena. He took something qualitative, the subjective experience of musical beauty, and found quantitative rules that govern it. This is exactly what we do in machine learning today, finding mathematical patterns in seemingly subjective or complex phenomena. When Spotify recommends a song you might like, it's using mathematical models of harmony, rhythm and structure that trace their lineage back to Pythagoras' monochord. The Pythagorean understanding of harmony also introduced the concept of discretization, taking continuous phenomena and representing them with discrete values. A vibrating string produces a continuous range of possible frequencies, but musical scales select specific discrete frequencies that sound pleasing together. This is analogous to how digital systems sample continuous analog signals at discrete time intervals, a process fundamental to all digital audio and signal processing. Consider how this plays out in modern technology. When you speak into your smartphone, your voice, a continuous pressure wave in the air, is sampled tens of thousands of times per second. Each sample is assigned a numerical value. These numbers are then processed, compressed, transmitted, and eventually reconstructed into sound at the other end. The entire process depends on the principle Pythagoras discovered, that sound can be represented mathematically. The Pythagorean scale, built entirely from perfect fifths, 3:2 ratios, dominated Western music for over 1,000 years. But it had a problem, one that wouldn't be fully solved until the time of Bauer, the Pythagorean comma. If you stack 12 perfect fifths, you should return to your starting note 7 octaves higher. But the math doesn't quite work out. You overshoot by a small interval called the Pythagorean comma. This mathematical quirk led eventually to the development of equal temperament, where the octave is divided into 12 equal semitones, a compromise that allows music to be played in any key. This musical problem is actually a profound mathematical one, touching on concepts like modular arithmetic and logarithms. The solution, equal temperament, requires each semitone to have a frequency ratio of the 12th root of 2, approximately 1.0546. This irrational number, which can't be expressed as a simple fraction, represents a departure from Pythagorean ideals but a triumph of practical mathematics. Every time a digital piano plays a note, it's calculating frequencies based on this mathematical compromise. The Pythagorean theorem, perhaps the most famous mathematical equation after E equals m times c squared, also has deep connections to computer science and digital signal processing. In its familiar form, a square plus b square equals c square. It describes the relationship between the sides of a right triangle. But this same relationship appears in countless computational contexts. When calculating distances in computer graphics, when processing signals in multiple dimensions, when training neural networks in high-dimensional spaces, we're using generalizations of the Pythagorean theorem. In digital signal processing, the Pythagorean theorem helps us understand phase relationships and signal power. When we perform a Fourier transform, breaking a complex sound into its component frequencies, we're using mathematics that builds on Pythagorean insights about harmony and frequency relationships. Every MP3 file on your device has been compressed using algorithms that depend on these mathematical principles. The Pythagorean concept of number also laid groundwork for computer science in unexpected ways. Pythagoreans distinguished between different types of numbers, odd and even, prime and composite, perfect and imperfect. They discovered that some numbers, like the square root of 2, couldn't be expressed as ratios of whole numbers, the irrational numbers. This classification of numbers prefigures type systems in programming languages, where different kinds of data are treated according to different rules. The Pythagorean fascination with perfect numbers equal to the sum of their proper divisors, like 6, that is 1 + 2, 3, 6, or 28, that is 1 + 2, 4, 7, 14, 28, might seem like mathematical curiosity, but the search for perfect numbers led to developments in number theory that now underpin cryptographic systems. When your browser establishes a secure connection, it's using properties of numbers that Pythagoreans first began exploring. Perhaps most remarkably, Pythagoras and his followers believed that understanding mathematical relationships was a path to understanding the divine order of the universe. They saw mathematics not as abstract manipulation of symbols, but as discovery of eternal truths. This philosophical stance, that mathematical truth exists independently of human minds and can be discovered through reason, underlies much of computer science. When we prove that an algorithm has certain properties, when we demonstrate that a problem is computationally intractable, we're engaging in the same kind of truth-seeking that Pythagoreans practiced. The Pythagorean influence extends even to the aesthetics of code. Programmers often speak of elegant solutions, of code that has a certain beauty or harmony. This isn't just metaphor. Well-structured code often exhibits mathematical properties like symmetry, recursion, and proportionality that Pythagoreans would have recognized as beautiful. The principle of don't repeat yourself, of DRY, in programming echoes the Pythagorean preference for unity and simplicity. As we prepare to leave Pythagoras and his harmonious mathematics, let's consider one final connection to modern computing. The Pythagorean discovery that music follows mathematical rules suggested that beauty itself might be computable. Today, AI systems compose music, create art, and even write poetry. These systems work by learning mathematical patterns in human-created works and generating new creations that follow similar patterns. Every AI-generated symphony is, in a sense, a vindication of the Pythagorean belief that harmony and beauty can be captured in numbers. Tonight, as you drift towards sleep, perhaps you'll hear the mathematical harmony in the world around you, the rhythmic patterns of your breathing, the periodic sounds of night, the hidden frequencies in the white noise of modern life. Remember that someone, 26 centuries ago, first heard these patterns and recognized them as mathematics, and in doing so, Pythagoras didn't just discover a property of music, he revealed a fundamental truth about the computational nature of reality itself. In our next chapter, we'll explore how Aristotle took the concept of logical reasoning and formalized it into a system of rules that would eventually become the Boolean algebra at the heart of every digital circuit, every if-then statement, every logical operation your computer performs billions of times each second. Chapter 3: Aristotle's Logic, the Blueprint for Boolean Algebra. In the Lyceum of Athens, around 350 BCE, a philosopher was teaching his students while walking through the covered walkways, the peripatos, from which his followers would take their name, the peripatetics. This philosopher was Aristotle, and what he was teaching would become nothing less than the foundation of all computational logic. Every if-then statement in every program ever written, every logic gate in every computer chip, every Boolean operation that determines the flow of billions of calculations per second, they all trace their lineage back to these afternoon walks in ancient Athens. Aristotle wasn't trying to invent computer science. He was trying to understand how humans think, how we reason from premises to conclusions, how we can be certain that our arguments are valid. In pursuing these questions, he created formal logic, a system of rules for valid reasoning that could be applied mechanically without regard to the content of the arguments themselves. This mechanical nature of logic, this ability to determine truth through systematic application of rules, is what makes computation possible. Let's begin with Aristotle's most famous contribution to logic, the syllogism. A syllogism is a form of reasoning where a conclusion is drawn from two premises. The classic example, though not actually from Aristotle himself, perfectly illustrates the concept. All men are mortal. Socrates is a man. Therefore Socrates is mortal. This might seem trivially obvious, but Aristotle's genius was in recognizing that the validity of this argument doesn't depend on its content. We could replace men, mortal, and Socrates with any other terms, and as long as the logical structure remains the same, the argument remains valid. In modern computational terms, Aristotle had discovered that reasoning could be abstracted from meaning. This is precisely what happens in a computer processor. When your CPU evaluates A and B or C, it doesn't know or care what A, B, and C represent. They could be anything: pixels in an image, characters in a text file, or control signals for a robot. The logical operations proceed the same way regardless. Aristotle's insight that form could be separated from content is what allows computers to be universal machines, capable of processing any kind of information. Aristotle identified several valid forms of syllogistic reasoning, which he called figures and moods. He systematically catalogued which combinations of premises could yield valid conclusions and which could not. This systematic approach, exhaustively enumerating all possibilities and determining which are valid, is exactly how we design digital circuits today. When engineers create a new processor instruction, they must consider all possible input combinations and determine the correct output for each. They are following Aristotle's method, just with silicon instead of syllables. The law of excluded middle, one of Aristotle's fundamental principles, states that for any proposition, either that proposition is true or its negation is true, there is no middle ground. In binary terms, everything is either 1 or 0, true or false, on or off. This principle is so fundamental to digital computing that we often forget it's a choice, not a necessity. Quantum computers, for instance, exploit superposition to exist in states that are neither purely 0 nor purely 1. But for the classical computers that run our world, Aristotle's excluded middle remains the bedrock principle. Another Aristotelian principle, the law of non-contradiction, states that contradictory statements cannot both be true at the same time. A bit cannot be simultaneously 0 and 1. A file cannot be both open and closed. A network packet cannot be both sent and unsent. This principle allows computers to maintain consistent state, to make definitive decisions, to produce reliable outputs. Without it, computation as we know it would be impossible. Consider how Aristotelian logic manifests in programming languages. Every if then else statement is a direct descendant of Aristotelian conditional reasoning. When you write, if user age 18, then grant access else deny access, you're implementing a syllogism in code. The computer, like an extremely fast and patient student of Aristotle, mechanically applies the logical rules to reach a conclusion. The Boolean algebra that George Boole developed in the 19th century, which forms the mathematical foundation of all digital circuits, is essentially Aristotelian logic expressed in mathematical notation. When Boole wrote his Investigation of the Laws of Thought, he was mathematizing principles that Aristotle had articulated 2 millennia earlier, and or not. These Boolean operators that process billions of times per second in your devices are performing operations that Aristotle would immediately recognize. Let's trace a specific example through history. Aristotle's modus ponens, if P implies Q and P is true, then Q must be true, appears in every digital circuit as the basis of signal propagation. When a logic gate receives a high signal, pulse P, and is configured to pass that signal when high, P implies Q, it outputs a high signal Q. The entire cascade of operations that occurs when you click a mouse button, from the electrical signal through the USB controller, through the operating system to the application, follows chains of modus ponens inferences, each component reasoning from its inputs to its outputs according to logical rules. Aristotle also grappled with problems that remain central to computer science today. His work on categories and classification prefigures object-oriented programming and type systems. When he organized knowledge into hierarchies, substance, quantity, quality, relation, and so on, he was creating something remarkably similar to class hierarchies in modern programming languages. The idea that objects can inherit properties from more general categories, that we can reason about groups of things with shared characteristics. These Aristotelian concepts are implemented millions of times in every object-oriented program. The Aristotelian concept of potentiality and actuality has surprising relevance to computing. A variable declared but not yet assigned has the potential to hold a value but hasn't actualized that potential. A function defined but not yet called exists in potentiality until the moment of execution brings it to actuality. Even the concept of lazy evaluation in functional programming, where computations are delayed until their results are needed, echoes Aristotle's distinction between what could be and what is. Aristotle's work on definitions and essential properties resonates through database design and data modeling. When database designers determine primary keys and establish relationships between tables, they're engaging in fundamentally Aristotelian analysis. What are the essential properties that define this entity? What relationships are necessary versus accidental? The entire practice of normalization in database design is an exercise in Aristotelian categorization. The debugging process itself follows Aristotelian methods. When a programmer encounters unexpected behavior, they reason through syllogisms. This function should return true when given valid input. The input is valid, therefore the function should return true, but it returns false. Therefore, either my premise about the input's validity is wrong, or my understanding of the function is incorrect. This systematic logical analysis, eliminating impossibilities until only the truth remains, is pure Aristotelian method. Even error handling in modern programming reflects Aristotelian logic. The try-catch-finally pattern implements a form of logical reasoning about exceptional cases. It says, try this operation. If it succeeds, proceed normally. If it fails in this specific way, handle it thus. If it fails in that specific way, handle it so. Finally, regardless of success or failure, ensure this cleanup occurs. This exhaustive case analysis, ensuring every logical possibility is addressed, would have delighted Aristotle. The concept of formal verification in software engineering, mathematically proving that a program behaves correctly, is perhaps the purest application of Aristotelian logic to computing. When we write formal specifications and prove that our implementation satisfies them, we're using logical deduction in exactly the way Aristotle envisioned. Tools like Coq, Isabelle, and TLA Plus allow us to construct mathematical proofs about our programs, ensuring with logical certainty that they behave as intended. As artificial intelligence has advanced, we've returned again and again to Aristotelian principles. Expert systems encode knowledge as logical rules, inference engines apply syllogistic reasoning, and even modern machine learning systems, for all their statistical complexity, often learn patterns that can be expressed as logical rules. When a neural network learns to classify images, it's discovering logical relationships between features, building its own syllogisms from data. The limits of Aristotelian logic also teach us important lessons about computation. Gödel's incompleteness theorems showed that any formal system complex enough to include arithmetic must be either incomplete or inconsistent. There are truths that cannot be proven within the system. The halting problem demonstrates that there are questions about programs that no program can answer. These fundamental limits, discovered in the 20th century, are boundaries that Aristotle himself might have anticipated, given his careful attention to the scope and limits of logical reasoning. As we close this chapter on Aristotelian logic, reflect on the remarkable journey from ancient Athens to modern Silicon Valley. Every time your computer makes a decision, every time a program branches based on a condition, every time a circuit processes a logical operation, it's implementing principles first articulated by a philosopher teaching his students among the columns of the Lyceum. The next time you write an if statement or design a Boolean expression, remember that you're participating in a tradition of formal reasoning that stretches back over 2 millennia. Tonight, as sleep approaches, perhaps you'll dream in syllogisms, your thoughts flowing through logical gates, premises leading inevitably to conclusions. And in your dreams, maybe you'll walk with Aristotle through those ancient colonnades, discussing not philosophy but functions, not metaphysics but methods, discovering together that the principles of thought he articulated would one day animate machines he could never have imagined. In our next chapter, we'll visit the Great Library of Alexandria, where the world's first librarians created systems for organizing and retrieving information that prefigure modern databases, search engines, and information architecture. Chapter 4, The Library of Alexandria, the First Database. In the year 295 BCE, on the shores of the Mediterranean, in the newly founded city of Alexandria, something unprecedented was taking shape. Ptolemy I, one of Alexander the Great's generals and now pharaoh of Egypt, had commissioned the construction of what would become the greatest information repository the ancient world had ever seen. The Library of Alexandria wasn't just a collection of scrolls, it was humanity's first systematic attempt to gather, organise, catalogue, and make searchable the entirety of human knowledge. In essence, it was the world's first database. Picture the library at its height. Hundreds of thousands of papyrus scrolls carefully stored in labelled container called capsae, arranged in 10 great halls, each dedicated to a different branch of knowledge. Scholars from across the Mediterranean world came here not just to read but to cross-reference, to discover connections, to build upon the work of others. The organisational challenges they faced and the solutions they developed would echo through history, eventually informing the design of modern databases, search engines and information retrieval systems. The mastermind behind the library's organisational system was Callimachus of Cyrene, a poet and scholar who served as the library's cataloguer around 245 BCE. Faced with the monumental task of organising hundreds of thousands of scrolls, Callimachus created something revolutionary: the Pinaquets, a 120-scroll catalogue that was essentially the world's first metadata system. The full title translates to tables of those who have distinguished themselves in every form of learning and what they wrote, a name that reveals its ambitious scope. The Pinax wasn't just a list, it was a sophisticated classification system. Callimachus divided all literature into genres: epic poetry, tragedy, comedy, history, medicine, mathematics, natural science, and miscellanea. Within each category, authors were listed alphabetically, and for each author, there was biographical information and a complete list of their works. For each work, Callimachus recorded the opening line, the total number of lines, and sometimes even critical notes about authenticity or quality. This is remarkably similar to modern database schemas, with tables, fields, primary keys, and relationships. Consider the computational sophistication of this approach. Callimachus had created what we would now call a relational database structure. Authors were entities with attributes, name, birthplace, biographical details. Works were separate entities with their own attributes, title, genre, length, opening line, and relationships to authors. The alphabetical ordering within categories provided what database designers call an index, a way to quickly locate specific information without searching through everything. The library's acquisition methods were equally systematic. Ships entering Alexandria's harbour were required to surrender any books they carried for copying. Scribes would create duplicates, keeping the originals for the library and returning the copies to the owners. This process, which the librarians called ship libraries, was essentially an early form of data harvesting and replication. The library also sent agents throughout the Mediterranean world to purchase or copy texts, creating what we might think of as distributed data collection nodes. But the Library of Alexandria was more than just a storage facility. It was a centre for information processing and knowledge creation. The scholars who worked there didn't just read texts. They compared different versions, identified errors, created critical editions, and wrote commentaries. They were performing what we now call data cleaning, validation, and enrichment. When Aristarchus of Samothrace created his critical edition of Homer, marking suspected interpolations with special symbols, he was essentially creating a version control system with annotations. The library's approach to dealing with multiple versions of the same text prefigures modern version control systems like Git. Scholars would maintain multiple copies of important works, noting variations between them. They developed a system of critical symbols, the asterisk to mark genuine but displaced lines, the obolus to mark spurious lines, that functioned like diff markers in modern code repositories. These marginalia were metadata about metadata, tracking the evolution and authenticity of information. Translation was another crucial function of the library. The famous translation of the Hebrew Bible into Greek, the Septuagint, was completed there. This massive translation project required coordination among multiple scholars, standardization of terminology, and quality control processes. It was, in essence, a large-scale data transformation project, converting information from one format, Hebrew, to another, Greek, while preserving semantic meaning. The physical architecture of the library also reflected sophisticated information design principles. The 10 halls weren't arbitrary divisions, but represented a hierarchical classification system. Within each hall, the capsae, scroll containers, were arranged systematically, with labels indicating their contents. Finding a specific work required navigating through multiple levels of organization, from hall to section to container to specific scroll. This hierarchical navigation is exactly how we traverse directory structures in modern file systems, or navigate through nested categories in databases. The library pioneered what we would now call information retrieval techniques. Scholars developed finding aids, lists, indices, and cross-references to help locate information across the vast collection. They created subject bibliographies, compiled lists of works on specific topics, and even developed primitive citation systems to reference other works. These tools allowed scholars to discover connections between different areas of knowledge, much like modern search engines reveal relationships between web pages. The social and collaborative aspects of the Library of Alexandria also presage modern information systems. The library was part of the larger Museum, Shrine of the Muses, where scholars lived and worked together. They engaged in peer review, collaborative research, and scholarly debate. This community of practice, sharing and building upon each other's work, mirrors modern open-source development communities and academic collaboration networks. The library's influence on standardization cannot be overstated. By collecting multiple versions of texts and creating authoritative editions, the library established standard versions that would be copied and transmitted throughout the ancient world. This standardization function is similar to how modern organizations like the WEC establish web standards or how RFC documents define internet protocols. Security and access control were also concerns at the Library of Alexandria. Not all scrolls were equally accessible. Some were restricted to senior scholars or required special permission to view. The library maintained careful records of who accessed what materials, creating what we would now call audit logs. The physical arrangement of the library, with different areas having different levels of access, implemented a primitive form of role-based access control. The library's approach to knowledge organization influenced classification systems for centuries to come. The division of knowledge into distinct disciplines, the alphabetical ordering within categories, the biographical approach to organizing works. These principles can be traced through medieval libraries, Renaissance encyclopedias, and into modern library science. The Dewey Decimal System and the Library of Congress classification are distant descendants of Callimachus's Pinaques. The tragic destruction of the Library of Alexandria, whether by fire, neglect, or gradual decline, represents one of history's greatest losses of information, but it also teaches us important lessons about data preservation and redundancy. The library's scholars understood this. They made copies of important works and sent them to other libraries. They were practicing what we now call backup and disaster recovery, though ultimately these measures weren't enough to preserve the collection. Modern search engines like Google can trace their conceptual roots back to the Library of Alexandria. The idea of crawling ship-surrendering books, indexing the PNX, ranking critical annotations, and retrieval finding aids were all present in nascent form. When PageRank algorithms analyze links between web pages to determine relevance, they're doing something conceptually similar to what Alexandrian scholars did when they trace citations and references between texts. As we close this chapter on the Library of Alexandria, let's reflect on its lasting legacy. Every time you query a database, search the web, or navigate a file system, you're using concepts that were first developed by ancient librarians facing the challenge of organizing humanity's knowledge. The Library of Alexandria showed us that information without organization is just noise, that knowledge builds upon knowledge, and that the systematic collection and classification of information is itself a form of computation. Tonight, as you drift towards sleep, imagine walking through those ancient halls, the smell of papyrus in the air, the whisper of scholars discussing their discoveries. Picture the endless rows of scrolls, each one a node in humanity's first great information network. The Library of Alexandria may be gone, but its vision of universal access to organized knowledge lives on in every database, every search engine, every attempt to make the world's information accessible and useful. In our next chapter, we'll explore how Euclid, working in this very library, developed an algorithm finding the greatest common divisor, a procedure so elegant and efficient that it's still used in modern cryptography, showing us that some algorithms are truly timeless. Chapter 5, Euclid's Algorithm, Ancient Recursion. In the Great Library of Alexandria around 300 BCE, a mathematician was writing what would become the most influential textbook in human history. Euclid, whose name would become synonymous with geometry, was compiling his masterwork, The Elements. But hidden within this geometric treatise was something that transcends geometry, an algorithm so elegant, so efficient, and so fundamental that it remains essentially unchanged in modern cryptographic systems. This is the Euclidean algorithm for finding the greatest common divisor, and it represents one of humanity's first formal algorithms, complete with the recursive thinking that defines modern computer science. Let's begin with the problem Euclid was trying to solve. Given two numbers, what is the largest number that divides both of them evenly? This greatest common divisor, or GCD, might seem like a simple mathematical curiosity, but it appears everywhere in computation. When you reduce a fraction to its simplest form, you're using the GCD. When your computer generates cryptographic keys for secure communication, it's using the GCD. When digital signal processors synchronize different clock rates, they are finding GCDs. This ancient algorithm runs billions of times every day in our modern digital infrastructure. Euclid's brilliant insight was that finding the GCD doesn't require factoring the numbers, a process that becomes impossibly slow for large numbers. Instead, he discovered a recursive relationship. The GCD of two numbers is the same as the GCD of the smaller number, and the remainder when the larger is divided by the smaller. In modern notation, GCD of A and B is equal to the GCD of B and modulo B. This simple observation leads to an algorithm of breathtaking elegance. Picture Euclid demonstrating this to his students in Alexandria. He might have used lengths of rope or marks on a sand table. Take two lengths, he would say, and repeatedly subtract the shorter from the longer until you cannot subtract any more. The length that remains is the common measure of both original lengths. What Euclid was describing was recursion, the process of solving a problem by reducing it to a simpler version of itself. Let's trace through an example as Euclid might have taught it. Finding the GCD of 48 and 18. First, divide 48 by 18, getting 2 with remainder 12. Now find the GCD of 18 and 12. Divide 18 by 12, getting 1 with remainder 6. Now find the GCD of 12 and 6. Divide 12 by 6, getting 2 with remainder 0. When the remainder is 0, the algorithm terminates, and the GCD is 6. This step-by-step reduction, each step simpler than the last, is the essence of recursive thinking. From a computer science perspective, Euclid's algorithm exhibits several remarkable properties. First, it's guaranteed to terminate. The remainders get strictly smaller with each step, so eventually we must reach 0. Second, it's incredibly efficient. The number of steps is logarithmic in the size of the input numbers. Third, it requires only basic arithmetic operations, division and finding remainders. These properties make it perfect for implementation in both ancient times and modern computers. The recursive nature of Euclid's algorithm was revolutionary, even if Euclid himself might not have thought of it in those terms. Recursion, the idea that a process can be defined in terms of itself, is fundamental to computer science. Every recursive function call in every programming language, every recursive data structure, every divide and conquer algorithm traces its intellectual lineage back to Euclid's method. Consider how naturally Euclid's algorithm translates to modern code. In Python, it's just a few lines. The implementation is virtually identical to Euclid's original description, separated by over 2 millennia. The algorithm's timeless elegance transcends programming languages, hardware architectures, and even number systems. The extended Euclidean algorithm, a variation that also finds coefficients expressing the GCD as a linear combination of the original numbers, is even more powerful. If GCD of A and B is equal to D, the extended algorithm finds integers x and y such that a times x plus b times y is equal to d. This seemingly abstract result is the foundation of modern public key cryptography. When your browser establishes a secure connection, it's using the extended Euclidean algorithm to compute modular multiplicative inverses essential for RSA encryption. The influence of Euclid's algorithm extends far beyond number theory. The algorithmic thinking it embodies, breaking complex problems into simpler sub-problems, appears throughout computer science. Dynamic programming, divide and conquer strategies, and recursive descent parsing all follow the pattern Euclid established. When a compiler parses your code, when a search algorithm explores a game tree, when a graphics engine renders a fractal, they're all using recursive decomposition inspired by Euclid's method. Euclid's algorithm also demonstrates the power of abstraction in mathematics and computing. The algorithm works not just for numbers, but for any mathematical objects that support division with remainder, polynomials, Gaussian, integers, even certain types of matrices. This abstraction, the ability to apply the same algorithm to different types of objects, prefigures the concept of generic programming and abstract data types in modern computer science. The efficiency of Euclid's algorithm has fascinated mathematicians for centuries. Gabriel Lemay proved in 1804 that the algorithm never requires more steps than 5 times the number of digits in the smaller number. This was one of the first algorithmic complexity analyses in history, predating the formal study of computational complexity by over a century. The worst-case inputs for Euclid's algorithm turn out to be consecutive Fibonacci numbers, revealing a beautiful connection between ancient Greek mathematics and medieval Italian number sequences. In the realm of computer algebra systems, Euclid's algorithm is the foundation for polynomial GCD computation, which is essential for symbolic mathematics. When software like Mathematica or Maple simplifies algebraic expressions, factors polynomials, or solves systems of equations, it's using generalizations of Euclid's algorithm. The same recursive principle that Euclid applied to integers now handles complex mathematical objects that would have seemed like magic to ancient mathematicians. The algorithm's role in cryptography cannot be overstated. The RSA encryption system, which secures much of our digital communication, relies on the difficulty of factoring large numbers while using Euclid's algorithm for key generation and decryption. Every time you make an online purchase, check your email or connect to a VPN, Euclid's algorithm is working behind the scenes, part of the mathematical machinery that keeps your data secure. Even in unexpected places, Euclid's algorithm appears. In computer graphics, it's used to generate Bresenham lines, the pixelated approximations of straight lines on your screen. In music theory, it helps analyze rhythmic patterns and generate Euclidean rhythms. In robotics, it assists in motion planning and gear ratio calculations. This ancient algorithm has found applications that Euclid could never have imagined. The teaching of Euclid's algorithm in computer science courses represents a bridge between ancient and modern knowledge. Students learning recursion often encounter Euclid's algorithm as one of their first examples, experiencing the same aha moment that Euclid students might have felt in Alexandria. The algorithm serves as a perfect introduction to recursive thinking, algorithmic analysis, and the timeless nature of mathematical truth. As we reflect on Euclid's algorithm, we see that it embodies principles that define good algorithm design even today: simplicity, efficiency, correctness, and broad applicability. Euclid showed us that an algorithm doesn't need to be complex to be powerful. Sometimes the most elegant solution is also the most effective, a lesson that every programmer learns but that Euclid understood over 2,000 years ago. The preservation of Euclid's algorithm through the ages, from papyrus scrolls to parchment manuscripts to printed books to digital files, represents the successful transmission of algorithmic knowledge across civilizations. Unlike physical artifacts that decay, algorithms are pure information, capable of perfect replication across time and space. Euclid's algorithm is as fresh and useful today as it was in ancient Alexandria. Tonight, as you prepare for sleep, consider the remarkable journey of this ancient algorithm. From the sandy floors of Alexandria, where Euclid might have traced the steps with a stick, to the silicon pathways of modern processors where it executes in nanoseconds, the algorithm remains essentially unchanged. It's a testament to the power of mathematical thinking and the universality of computational principles. In our next chapter, we'll explore how Archimedes used iterative methods to approximate pi, developing techniques of numerical analysis that would eventually enable computers to calculate billions of digits of this mysterious constant. Chapter 6: Archimedes' method of exhaustion, protocalculus, and iteration. In Syracuse, on the island of Sicily, around 250 BCE, a man was so absorbed in drawing geometric figures in the sand that he didn't notice the Roman soldier approaching. "Do not disturb my circles," Archimedes supposedly said, his last words before the soldier's sword fell. But the circles Archimedes was contemplating weren't just geometric curiosities. They represented one of humanity's first systematic approaches to numerical approximation, a method that would eventually evolve into the iterative algorithms that power modern scientific computing. Archimedes' method of exhaustion was his technique for calculating areas and volumes by inscribing and circumscribing polygons around curves. systematically increasing the number of sides to exhaust the space between the approximation and the true value. This wasn't just geometry, it was an algorithm, a computational procedure that could be repeated to achieve any desired level of precision. In modern terms, Archimedes had invented iterative refinement, the foundation of numerical analysis. Let's explore his most famous application, approximating pi. Archimedes began with a circle and inscribed a hexagon inside it, then circumscribed another hexagon around it. He could calculate the perimeters of these hexagons exactly, giving him lower and upper bounds for the circle's circumference. But here's where the magic happens. By doubling the number of sides to create 12 gons, then 24 gons, then 48 gons, and finally 96 gons, he systematically tightened these bounds, squeezing pi between increasingly precise limits. Picture Archimedes at work, perhaps using a compass and straight edge on a wax tablet, carefully calculating. For the 96-sided polygons, he determined that pi must be greater than 223 over 71, approximately 3.148, and less than 22 over 7, approximately 3.1429. This gave pi correct to 2 decimal places, a remarkable achievement using only basic arithmetic and geometric reasoning. But more importantly, he had demonstrated a method that could, in principle, calculate pi to any desired accuracy. From a computational perspective, Archimedes' method embodies several fundamental concepts. First, it's iterative. Each step builds upon the previous one, refining the approximation. Second, it provides error bounds. We know how close our approximation is to the true value. Third, it is convergent, meaning that with each iteration we get closer to the exact answer. These 3 properties define what computer scientists call a good numerical algorithm. The method of exhaustion wasn't limited to circles. Archimedes used it to find the area under a parabola, discovering that it's exactly 4 over 3 the area of an inscribed triangle, a result that wouldn't be reproven until the invention of calculus nearly 2 millennia later. He calculated the surface area and volume of spheres, the volumes of segments of paraboloids and hyperboloids, and even tackled the spiral that now bears his name. Each calculation required inventing new iterative techniques, new ways of exhausting the space between approximation and reality. Consider how this approach manifests in modern computing. When your GPS calculates your position, it uses iterative methods to refine its estimate based on satellite signals. When weather simulations predict tomorrow's forecast, they're using iterative numerical methods to solve differential equations. When machine learning algorithms train neural networks, they iteratively adjust weights to minimize error. The principle Archimedes established, systematic refinement through iteration, underlies virtually all numerical computation. Archimedes also understood something crucial about computational complexity. He realized that doubling the number of polygon sides roughly doubled the computational work, but didn't double the accuracy. This is an early recognition of what we now call diminishing returns in numerical algorithms, a fundamental trade-off between computational cost and precision that every programmer must consider. The calculations Archimedes performed were prodigious for his time. Working with 96-sided polygons meant handling square roots of large numbers, which he computed using what we would now recognize as a form of the Babylonian method, itself an iterative algorithm for finding square roots. He was essentially running nested iterations, an outer loop refining the polygon approximation and inner loops computing the necessary square roots. This hierarchical structure appears everywhere in modern scientific computing. Archimedes' work on the method of exhaustion also touched on what we now call numerical stability. He carefully chose his calculation sequence to avoid accumulating rounding errors. Though he worked with fractions rather than decimals, the principle is the same. When he computed perimeters of inscribed and circumscribed polygons, he used formulas that maintained accuracy even as the number of sides increased. This attention to numerical precision presages the entire field of numerical analysis. The philosophical implications of Archimedes' method are profound. He showed that infinity could be approached through finite means, that the continuous could be approximated by the discrete. This is exactly what happens when we digitize analog signals, when we approximate smooth curves with pixels, when we simulate continuous physics on discrete computers. Archimedes proved that with enough iteration, we can get arbitrarily close to truth, a principle that underlies all of digital approximation. Let's trace a specific example through history. Archimedes' method for computing pi inspired later mathematicians to develop increasingly sophisticated iterative algorithms. In the 15th century, Madhava of Sangamagrama used infinite series, essentially taking Archimedes' iteration to its logical limit. In the 17th century, Newton and Leibniz formalized these ideas into calculus. In the 20th century, computers implemented these algorithms to calculate billions of digits of pi. The Chudnovsky algorithm used to compute trillions of digits of pi is a direct descendant of Archimedes' iterative approach. The method of exhaustion also prefigures Monte Carlo methods in computing. While Archimedes used deterministic approximations, the idea of approaching a difficult calculation through many simpler ones is the same. When modern computers simulate particle physics, model financial markets, or render photorealistic graphics, they are using statistical versions of exhaustion, throwing computational resources at a problem until the answer emerges from the accumulation of approximations. Archimedes' approach to problem solving, breaking complex problems into sequences of simpler calculations, is fundamental to algorithm design. When we use dynamic programming to solve optimization problems, when we implement divide and conquer algorithms, when we design recursive procedures, we're following the pattern Archimedes established. Complex problems yield to systematic decomposition and iterative refinement. The error analysis that Archimedes performed was remarkably sophisticated. He didn't just calculate approximations, he proved bounds on how far these approximations could be from the true value. This is exactly what modern numerical analysts do when they prove convergence rates for iterative algorithms. The notation may have changed, but the fundamental approach, providing mathematical guarantees about computational procedures, remains the same. Even Archimedes' famous Eureka moment, discovering the principle of buoyancy while bathing, has computational significance. The story illustrates the sudden insight that can come from reconceptualizing a problem, seeing it from a different angle. In computer science, we call these aha moments paradigm shifts, when a problem that seemed intractable suddenly becomes solvable through a change in perspective. The bathtub insight led Archimedes to a new method for calculating volumes of irregular objects, essentially an analog computer using water displacement. The preservation and transmission of Archimedes' methods is itself a fascinating story. His works were copied and recopied through the centuries, translated from Greek to Arabic to Latin, each transmission potentially introducing errors but keeping the core algorithms alive. The recent discovery of the Archimedes palimpsest, a medieval manuscript containing previously unknown works, shows that even now we're still discovering the full extent of his computational thinking. As we prepare to leave Archimedes and his circles in the sand, let's reflect on his lasting contribution to computational thinking. He showed us that perfection can be approached through imperfection, that the infinite can be grasped through the finite, that systematic iteration can solve problems that seem impossibly complex. Every numerical simulation, every iterative solver, every approximation algorithm traces its intellectual lineage back to Archimedes' method of exhaustion. Tonight, as you drift towards sleep, imagine Archimedes at his sand table, inscribing polygon after polygon, each one closer to the perfect circle, never quite reaching it but always approaching. This is the essence of numerical computation, the endless pursuit of precision through repetition, the dance between the discrete and the continuous, the eternal iteration toward truth. In our next chapter, we'll explore how Eratosthenes developed his famous sieve for finding prime numbers, creating an algorithm so elegant and efficient that it's still taught in every computer science curriculum, showing us how systematic elimination can be more powerful than direct calculation. Chapter 7, The Sieve of Eratosthenes, Algorithmic Thinking, in the city of Cyrene, on the coast of modern-day Libya, around 26 BCE, a polymath was contemplating the nature of numbers. Eratosthenes, who would later become the chief librarian at Alexandria, was about to devise an algorithm so elegant, so efficient, and so fundamentally sound that it would be taught, essentially unchanged, in computer science courses over 2 millennia later. The Sieve of Eratosthenes, a method for finding all prime numbers up to a given limit, represents one of humanity's first examples of what we now call algorithmic optimization, achieving maximum efficiency through systematic elimination rather than direct computation. Picture Eratosthenes with a tablet of wax or perhaps a sand table, marking out the natural numbers from 2 to say 100. His insight was brilliantly simple. Instead of testing each number individually to see if it's prime, why not eliminate all the composite numbers and see what remains? Start with 2, the first prime, mark all its multiples 4, 6, 8 and so on as composite. Move to the next unmarked number, 3, mark all its multiples, continue this process, and when you're done, the unmarked numbers are precisely the primes. The beauty of this algorithm lies in its efficiency. To understand why, consider the alternative, testing each number for primality by checking if it's divisible by any smaller number. For a number n, this requires checking roughly n divisions. But the sieve eliminates composites in batches, marking off multiples in simple arithmetic progressions. The computational savings are enormous, especially as numbers grow larger. From a computer science perspective, the Sieve of Eratosthenes demonstrates several fundamental algorithmic principles. First, it shows the power of pre-processing, doing work up front to make later queries fast. Second, it exemplifies space-time trade-offs, using memory to store the sieve, to save computation time. Third, it introduces the concept of batch processing, handling multiple items together rather than individually. These principles appear throughout modern computing, from database indexing to compiler optimization. Let's trace through the algorithm as Eratosthenes might have performed it. Starting with numbers 2 through 30, begin with 2, mark off 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. Move to 3, mark off 6 already marked, 9, 12 already marked, 15, 18 already marked, 21, 24 already marked, 27, 30 already marked. Move to 5, mark off 10 already marked, 15 already marked, 20 already marked, 25, 30 already marked. The next unmarked number is 7. 7, but 7 squared is 49, which exceeds 30, so we're done. The primes up to 30 are 2, 3, 5, 7, 11, 13, 17, 19, 23, 29. Notice that optimization Eratosthenes discovered. We only need to sieve up to the square root of our limit. Why? Because if a number n has a factor greater than its square root, it must also have a corresponding factor less than its square root. This square root optimization reduces the algorithm's complexity dramatically, from quadratic to logarithmic, one of the most efficient algorithms for finding multiple primes. The Sieve also demonstrates the principle of lazy evaluation, though Eratosthenes wouldn't have called it that. When marking multiples of a prime p, we don't need to start at 2 times p or 3 times p. We can start at p squared. Why? Because all smaller multiples have already been marked by smaller primes. This optimization, discovered over 2,000 years ago, is exactly the kind of algorithmic refinement that modern programmers seek. In modern computing, the Sieve of Eratosthenes appears in numerous applications. Cryptographic systems need large primes for key generation. The Sieve, or its variants, helps identify prime candidates quickly. Computer algebra systems use it for factorization algorithms. Even in unexpected places like generating hash functions or designing error-correcting codes, the systematic approach of the Sieve proves useful. The Sieve's influence extends beyond prime finding. The algorithmic pattern, systematically eliminating possibilities until only the desired elements remain, appears throughout computer science. In constraint satisfaction problems, we eliminate invalid assignments. In branch and bound algorithms, we prune search spaces. In database query optimization, we filter out irrelevant records early. The Sieve taught us that elimination can be more efficient than construction. Consider the memory access patterns of the Sieve. As we mark off multiples, we're accessing memory in regular strides, every second element, every third element, and so on. This predictable access pattern is cache-friendly on modern processors, making the ancient algorithm surprisingly well-suited to contemporary hardware architectures. Eratosthenes accidentally designed an algorithm that would perform well on computers that wouldn't exist for 2 millennia. The Sieve also introduces concepts of parallel computation. Different parts of the Sieve can be computed independently. One processor could mark multiples of 2 while another marks multiples of 3. This embarrassingly parallel structure makes the Sieve attractive for modern parallel computing environments. GPU implementations of the Sieve can find billions of primes in seconds, using the same fundamental algorithm Eratosthenes devised with sand and stylus. Variants of the Sieve have been developed over the centuries, each adding new optimizations while preserving the core idea. The segmented Sieve breaks the range into chunks, allowing us to find primes in ranges that wouldn't fit in memory. The wheel Sieve skips numbers that are obviously composite, like even numbers except 2. The Sieve of Atkin, a modern variant, uses quadratic forms to identify primes even more efficiently. Yet all these variants build upon Eratosthenes' fundamental insight. Systematic elimination beats individual testing. The educational value of the Sieve of Eratosthenes cannot be overstated. It's often one of the first algorithms students implement when learning programming. The algorithm is simple enough to understand immediately, yet rich enough to support numerous optimizations. Students learn about array manipulation, loop optimization, and algorithmic complexity, all through this ancient algorithm. It bridges the gap between mathematical theory and practical programming. The Sieve also teaches us about the limits of optimization. While we can improve the constant factors, the fundamental complexity of finding primes remains. This is related to deep questions in number theory, the distribution of primes, the Riemann hypothesis, the twin prime conjecture. Eratosthenes' simple algorithm touches on some of mathematics' greatest unsolved problems. From a philosophical perspective, the Sieve represents a shift from direct to indirect thinking. Instead of asking, "Is this number prime?" for each number, Eratosthenes asked, "Which numbers are definitely not prime?" This inversion of perspective, solving a problem by considering its complement, is a powerful problem-solving technique that appears throughout computer science and mathematics. The Sieve's influence on data structure design is subtle but important. The algorithm naturally leads to the concept of a bit vector, a compact representation where each bit indicates whether a number is prime. This data structure, using one bit per number instead of storing the numbers themselves, demonstrates space-efficient representation of sets. Modern databases use similar techniques with bitmap indexes to efficiently query large datasets. Eratosthenes himself was a remarkable polymath. He calculated the Earth's circumference with stunning accuracy, created the first map of the world with latitude and longitude lines, and coined the term geography. His algorithmic thinking in the Sieve reflects the same systematic, methodical approach he applied to all his investigations. He showed that complex problems yield to careful, systematic analysis. The preservation of the Sieve of Eratosthenes through history is a testament to its fundamental importance. Unlike physical inventions that can be lost or forgotten, algorithms are pure ideas that can be rediscovered. Indeed, the Sieve has probably been independently rediscovered countless times. Its simplicity and elegance make it almost inevitable. Given the problem of finding primes, the Sieve emerges naturally. As we close this chapter on the Sieve of Eratosthenes, let's appreciate its lasting legacy. Every time a cryptographic key is generated, every time a primality test is performed, every time a student learns about algorithmic efficiency, Eratosthenes' ancient algorithm continues its work. It reminds us that the best algorithms are often the simplest, that systematic approaches beat brute force, and that insights from antiquity can remain relevant in the digital age. Tonight, as you prepare for sleep, imagine Eratosthenes at his hand table, methodically crossing out numbers, watching the primes emerge like islands in a sea of composites. Picture the satisfaction he must have felt seeing the pattern emerge, the primes revealing themselves not through calculation but through elimination. This is the joy of algorithmic discovery, finding an elegant solution that transforms a hard problem into an easy one. In our next chapter, we'll explore Hero of Alexandria's mechanical marvels, programmable automata that performed complex sequences of actions, showing us that the concept of program behavior predates electronics by 2,000 years. Chapter 8. Heroes Automata, the first programmable robots. In Alexandria, around 60 CE, an inventor was creating machines that seemed to possess a spark of life. Hero of Alexandria, also known as Heron, was designing automata, self-operating machines that could perform complex sequences of actions without human intervention. These weren't simple mechanical toys, but sophisticated programmable devices that implemented what we would now recognize as sequential control system, conditional logic, and even primitive forms of stored programs. In Hero's workshop, the concept of programmed behavior was born, 2,000 years before the first electronic computer. Picture Hero's most famous creation, a miniature theatre that performed an entire play automatically. When activated, doors would open to reveal the stage. Figures would move across the scene depicting the myth of Dionysus. Ships would sail across painted waves. Thunder would sound at dramatic moments. Doors would close and reopen to show different scenes. All of this happened through an intricate system of ropes, weights, counterweights, and carefully calibrated mechanisms, a mechanical program executing a predetermined sequence of instructions. The key to Hero's automata was a remarkable innovation, the programmable cam. By wrapping rope around a cylinder with pegs at specific positions, Hero could encode a sequence of actions. As the cylinder rotated, driven by a falling weight, the pegs would pull strings at precise moments, triggering different mechanisms. This is fundamentally the same principle as a music box or a player piano, but Hero was using it to create complex programmed behaviors. In modern terms, the cylinder was read-only memory, or M, the pegs were the program, and the ropes and mechanisms were the output devices. Consider the computational sophistication of this approach. Hero had created a system where timing, sequence, and action were encoded in physical form. The position of each peg determined when an action would occur. The arrangement of multiple pegs created complex sequences. By changing the peg positions, the program could be modified. This is exactly analogous to how modern computers store programs, as patterns of bits, that determine what operations occur when. Hero's automatic temple doors represent another breakthrough in programmed behavior. When a fire was lit on the temple altar, the heat would cause air in a hidden chamber to expand, pushing water through pipes that would turn wheels and open the doors. When the fire was extinguished, the process would reverse, closing the doors. This wasn't just automation, it was conditional behavior. If fire is present, then open doors, else close doors. Hero had implemented a mechanical if-then statement, the fundamental building block of all programming logic. The hydraulic and pneumatic systems Hero designed demonstrate an understanding of what we now call feedback control. His automatic wine dispenser would pour a predetermined amount of wine when a coin was inserted, an early vending machine. But more importantly, it used the weight of the wine itself to close the valve when the correct amount had been dispensed. This self-regulating behavior, where the output affects the control mechanism, is the principle behind everything from thermostats to cruise control to machine learning algorithms that adjust their parameters based on results. Hero's work on pneumatics and hydraulics also established principles of power transmission and signal propagation that would later appear in computing. His designs showed how pressure changes could propagate through tubes to trigger distant mechanisms, analogous to how electrical signals propagate through wires in modern computers. He demonstrated that complex behaviors could emerge from simple components connected in specific ways, a principle fundamental to both mechanical and electronic computation. Let's examine Hero's Hercules and the Dragon automaton in detail. When activated, Hercules would draw his bow and shoot an arrow at a dragon, which would then hiss and collapse. This sequence required precise coordination. The bow-drawing mechanism had to complete before the arrow release, the hiss had to coincide with the arrow's impact, and the collapse had to follow the hiss. Hero achieved this through a cascade of triggered events, each mechanism activating the next in sequence. This is exactly how modern computers execute instructions, one operation completing and triggering the next in a carefully orchestrated sequence. The programmability of Hero's devices extended beyond simple sequences. His designs included branching mechanisms, devices that could follow different paths based on conditions. His automatic theatre could perform different plays by reconfiguring the ropes and pegs. This reconfigurability is what distinguishes a programmable device from a merely automatic one. It's the difference between a clock, which always performs the same function, and a computer, which can be programmed to perform different tasks. Hero's influence on later automaton makers was profound. The Byzantine Empire continued his tradition with elaborate mechanical throne rooms that awed visitors. Islamic engineers like Al-Jazari expanded on Hero's principles to create even more sophisticated programmable machines. The mechanical clocks of medieval Europe, with their complex astronomical displays and animated figures, were direct descendants of Hero's work. Each generation built upon his fundamental insight that complex behavior could be encoded in mechanical form. The preservation and transmission of Hero's work is a fascinating story in itself. His treatises on pneumatics and mechanics were copied and translated through the centuries, inspiring inventors from Baghdad to Venice. During the Renaissance, Hero's designs were reconstructed and improved upon. The elaborate automata of the 18th century, Vaucanson's mechanical duck, Jacques Droz's writing automaton, were sophisticated elaborations of principles Hero had established. From a computer science perspective, Hero's automata demonstrate several key concepts. First, they show that computation doesn't require electricity or electronics. It only requires a systematic way to process information and control behavior. Second, they illustrate the principle of abstraction. Complex behaviors built from simple reusable components. Third, they embody the concept of stored programs, instructions encoded in physical form that determine machine behavior. The entertainment aspect of Hero's automata shouldn't obscure their computational significance. By creating machines that could tell stories, Hero was grappling with problems of representation and sequencing that remain central to computer science. How do you encode narrative in mechanical form? How do you ensure events happen in the correct order? How do you create the illusion of purposeful behavior from deterministic mechanisms? These questions resonate through game design, animation, and artificial intelligence. Hero's mathematical work also contributed to computational thinking. His formula for calculating the area of a triangle from its side lengths, often called Heron's formula, demonstrates algorithmic thinking applied to geometry. His work on reflection and refraction of light laid groundwork for optics. His investigations into mechanical advantage and gear ratios provided tools for designing efficient mechanisms. All of these contributions show a mind that thought systematically about transforming inputs to outputs, the essence of computational thinking. The philosophical implications of Hero's automata were profound and controversial. If machines could mimic life, what distinguished living beings from clever mechanisms? This question, first raised by Hero's creations, would echo through Descartes' mechanical philosophy, La Maîtrise man-a-machine, and ultimately to modern debates about artificial intelligence and consciousness. Hero's automata forced humanity to confront the possibility that behavior we consider intelligent or purposeful might arise from purely mechanical processes. Modern robotics can trace its lineage directly to a Hero's workshop. The principles he established, sequential control, conditional behavior, feedback mechanisms, programmability, remain fundamental to robotics today. When a modern industrial robot performs a complex assembly task, it's following a programmed sequence just like Hero's automatic theatre. When a Mars rover navigates terrain autonomously, it's using conditional logic that Hero would recognise. The materials have changed from ropes and bronze to silicon and steel, but the principles remain remarkably consistent. As we close this chapter on Hero's automata, let's appreciate the profound leap of imagination they represented. In a world without electricity, without precision manufacturing, without computer science as a discipline, Hero created machines that embodied computational principles we still use today. He showed that programming is not about the medium but about the logic, that behavior can be encoded, stored and executed whether in rope and pegs or in bits and bytes. Tonight, as you drift towards sleep, imagine Hero's workshop in ancient Alexandria, gears turning, water flowing through hidden pipes, mechanical figures dancing through their prescribed routines. Picture the wonder of ancient audiences watching these machines come to life, not knowing they were witnessing the birth of programmed behavior. And remember that every robot, every automated system, every programmed device traces its ancestry back to this ancient inventor who first asked, "Can we make machines that act on their own?" In our next chapter, we'll explore the cryptographic innovations of ancient Greece, the Cytel and Polybius square, showing how the need for secret communication led to the development of encryption techniques that prefigure modern cryptography. Chapter 9. Greek Cryptography, the Cytel and Polybius square. In the shadows of ancient warfare where messages could determine the fate of cities and empires, the Greeks developed sophisticated methods for protecting information. Around 500 BCE, Spartan military commanders were using a device called the cytela, a wooden rod around which a strip of leather or parchment was wound to encrypt their battlefield communications. Meanwhile, the historian Polybius was devising a square cipher that would influence cryptographic thinking for millennia. These weren't just clever tricks for hiding messages, they were systematic approaches to information transformation that embody fundamental principles of modern cryptography. Picture a Spartan commander preparing to send orders to distant troops. He wraps a strip of leather spirally around a wooden rod of specific diameter, the cytale, writing his message along the length of the rod, one letter per wrap. He creates what appears to be a meaningless sequence when the leather is unwound. Only someone with an identical rod can rewrap the strip and read the message. This is transposition cipher in its purest form. The information isn't changed, just rearranged according to a systematic rule. The cytale demonstrates several key cryptographic concepts. First, it separates the algorithm, the method of encryption, from the key, the rod's diameter. This separation, formalized by August Kirchhoffs in the 19th century, remains a cornerstone of cryptographic design. Second, it shows that security can come from permutation, rearranging information rather than substituting it. Third, it illustrates the importance of standardization. Both sender and receiver need identical rods, just as modern cryptographic systems require shared keys or parameters. From a computational perspective, the cytale performs what we would now call a columnar transposition. If the rod accommodates in letters around its circumference, the message is effectively written in rows of letters, then read column by column. This transformation can be expressed mathematically. If position is in the plaintext becomes position j in the ciphertext can be calculated using a simple function. The Greeks had discovered algorithmic encryption without the mathematical notation to express it formally. The Polybius square, developed around 200 BCE, took a different approach. Polybius arranged the Greek alphabet in a 5x5 grid, combining 2 letters to fit 24 letters into 25 spaces. Each letter could then be represented by its row and column numbers. The letter alpha might be 11, row 1, column 1, beta 12, and so on. This simple substitution had profound implications. It converted alphabetic information into numeric form, enabling new forms of manipulation and transmission. Consider the elegance of Polybius's system. By reducing the alphabet to pairs of numbers from 1 to 5, he had performed what computer scientists call encoding, transforming data from one representation to another. This numeric encoding enabled various transmission methods: torch signals, one torch for row, pause, then torches for column, drum beats, or even prisoners tapping on walls. The Polybius square was an early example of digital communication, converting continuous information into discrete symbols. The Polybius square also enabled more complex cryptographic operations by applying transformations to the numeric pairs, adding a constant, multiplying by a factor, or rearranging the grid itself. Greeks could create increasingly sophisticated ciphers. This layering of transformations, where the output of one operation becomes the input to another, is fundamental to modern cryptographic design. The Data Encryption Standard, DES, and Advanced Encryption Standard, AES, use exactly this principle. Multiple rounds of substitution and permutation. Greek cryptography extended beyond military applications. The ancient Greeks used cryptographic techniques in religious mysteries, hiding sacred knowledge from the uninitiated. They employed steganography, hiding the existence of messages rather than just their content. Histiaeus tattooed a message on a slave's shaved head, waited for the hair to regrow, then sent the slave to deliver the hidden message. Demaratus scraped wax from wooden tablets, wrote warnings about Persian invasion plans, then recovered them with wax to appear blank. These steganographic methods reveal sophisticated thinking about information hiding. The Greeks understood that security could come from obscurity, hiding that a message exists, as well as from encryption, hiding what a message says. Modern digital watermarking, where copyright information is invisibly embedded in images or audio, follows the same principle. When your printer adds nearly invisible yellow dots to every page for forensic tracking, it's using steganography invented by the ancient Greeks. The Greeks also pioneered cryptanalysis, the art of breaking codes. The frequency analysis of letters, though fully developed by Arab scholars, has roots in Greek linguistic studies. Greek scholars noticed that certain letters appeared more frequently than others in their language, observation that would eventually become the key to breaking substitution ciphers. They understood that patterns in language create vulnerabilities in encryption, a principle that drives modern cryptanalysis. Authentication was another Greek cryptographic innovation. The Spartans used a system of sealed messages where the seal's pattern served as both tamper evidence and sender verification. This is conceptually identical to modern digital signatures, cryptographic techniques that verify both message integrity and sender identity. When you receive a software update that's digitally signed, you're using a more sophisticated version of the Spartan seal system. The Greek approach to key distribution presages one of cryptography's hardest problems. How do you securely share the rod diameter for a cytel, or the grid arrangement for a Polybius square? The Greeks used trusted couriers, prearranged meetings, and even hereditary knowledge passed down through families. These solutions mirror modern approaches. Trusted certificate authorities, key exchange protocols, and hardware security modules all address the same fundamental challenge the Greeks faced. Greek cryptography also touched on information theory concepts that wouldn't be formalized until Claude Shannon's work in the 20th century. The Polybius square's conversion of 24 letters into pairs of 5 symbols is a form of encoding that balances efficiency with redundancy. The cytel's transposition preserves all information while maximizing confusion. These techniques show intuitive understanding of concepts like entropy, redundancy, and the confusion-diffusion paradigm that underlies modern cipher design. The influence of Greek cryptographic thinking extends far beyond ancient times. The Polybius square inspired numerous historical ciphers, including the nihilist cipher used by Russian revolutionaries and the EDVGVX cipher used in World War I. The principle of transposition used in the Citali appears in modern block ciphers and hash functions. Even quantum cryptography, with its focus on physical properties ensuring security, echoes the Greek idea that the physical characteristics of the C-tail rod provided protection. The Greeks understood that cryptography was about more than just military advantage. It was about controlling information flow in society. They used cryptographic techniques to protect trade secrets, diplomatic correspondence, and philosophical teachings. This broad application of cryptography presages our modern information society, where encryption protects everything from credit card transactions to private messages to medical records. The mathematical foundations laid by Greek mathematicians also contributed to cryptography. Euclid's work on prime numbers and greatest common divisors would eventually become crucial for public key cryptography. The Greek fascination with number theory, perfect numbers, prime numbers, geometric progressions, provided tools that modern cryptographers use to create unbreakable codes. When RSA encryption uses the difficulty of factoring large numbers, it builds on mathematical foundations the Greeks established. The preservation of Greek cryptographic knowledge through Byzantine and Islamic scholars ensured these techniques survived to influence Renaissance cryptographers. The Arabic scholars who translated Greek texts added their own innovations, creating a continuous tradition of cryptographic development. This transmission of knowledge across cultures and centuries shows how cryptographic ideas, like mathematical truths, transcend their original context. As we close this chapter on Greek cryptography, let's appreciate how these ancient techniques established principles that remain central to information security. The separation of algorithm and key, the use of transposition and substitution, the importance of authentication, the challenge of key distribution. All these concepts, first explored by the Greeks, remain fundamental to protecting information in our digital age. Tonight, as you drift towards and sleep, imagine those ancient Greek messages, leather strips wound around wooden rods, letters arranged in secret squares, warnings hidden beneath wax tablets. Picture the ingenuity required to protect information without computers, without advanced mathematics, with only clever thinking and systematic methods. Remember that every encrypted message sent today, every secure connection established, every piece of protected data builds upon cryptographic principles the ancient Greeks discovered. In our final chapter, we'll explore the lasting legacy of Greek computational thinking, showing how these ancient innovations, from mechanical computers to algorithms to cryptography, laid the foundation for our modern digital world. Chapter 10: The Legacy: How Greek Ideas Shape Modern Computing. As we reach the end of our journey through ancient Greece, let's pause to appreciate the profound and lasting impact these ancient thinkers have had on our digital age. From the bronze gears of the Antikythera mechanism to the abstract logic of Aristotle, from the iterative methods of Archimedes to the cryptographic innovations of the Spartans, the Greeks laid foundations that support the entire edifice of modern computing. Tonight, as you prepare for peaceful sleep, let's weave together these threads and see how they form the fabric of our computational world. Consider your smartphone, that marvel of modern technology resting on your nightstand. Within its circuits run algorithms descended from Euclid's ancient method for finding greatest common divisors. Its encryption protocols build upon principles first explored with the Spartan C-tail. Its digital audio processing echoes Pythagoras' discoveries about harmonic ratios. Its logical operations follow rules Aristotle formulated. Even its calendar calculations trace back to the astronomical computations of the Antikythera mechanism. This device, which seems so thoroughly modern, is actually the culmination of ideas that began in ancient Greece. The Greek approach to problem-solving, systematic, logical, and abstract, established the intellectual framework for computer science. When the Greeks insisted on proving mathematical theorems rather than just observing patterns, they created the concept of algorithmic correctness. When they developed formal logic, they provided the theoretical foundation for digital circuits. When they organized knowledge in the Library of Alexandria, they pioneered information architecture. These weren't just ancient achievements, they were the seeds of computational thinking. Let's trace how Greek ideas evolved into modern computing through the centuries. The preservation of Greek texts through Byzantine and Islamic scholars ensured these ideas survived the fall of Rome. Arab mathematicians like Al-Khwarizmi, whose name gives us the word algorithm, built upon Greek foundations. Renaissance thinkers rediscovered Greek texts and applied them to new problems. The scientific revolution used Greek mathematical methods to unlock nature's secrets. Each generation added layers of sophistication, but the Greek foundation remained. When Charles Babbage designed his analytical engine in the 1830s, he was implementing ideas that would have been familiar to Hero of Alexandria: programmable sequences, conditional operations, and mechanical computation. When George Boole developed Boolean algebra, he was formalizing logical principles Aristotle had outlined. When Alan Turing conceived the theoretical foundation of computer science, he was extending the Greek tradition of abstract mathematical reasoning. The path from ancient Greece to modern computing is direct and unbroken. The influence of Greek computational thinking extends beyond technology to shape how we understand intelligence itself. When we debate whether machines can think, we're continuing a conversation that began with Hero's automata. When we use the Turing test to evaluate artificial intelligence, we're applying Greek philosophical methods to modern questions. When we design neural networks that learn from experience, we're implementing ideas about knowledge and reasoning that Greek philosophers first explored. Consider how Greek algorithms remain essentially unchanged in modern use. The Sieve of Eratosthenes, invented around 276 BCE, is still one of the most efficient ways to find prime numbers. Euclid's algorithm from 300 BCE is still the standard method for computing greatest common divisors. Archimedes' iterative approximation methods from 250 BC underlie modern numerical analysis. These algorithms have survived not as historical curiosities, but as practical tools, their elegance and efficiency unmatched after 2 millennia. The Greek emphasis on proof and logical rigor established standards that define computer science today. When programmers verify their code's correctness, when cryptographers prove their system security, when algorithm designers analyze computational complexity, they're following Greek traditions. The insistence on mathematical certainty, on understanding why something works, rather than just observing that it does, comes directly from Greek mathematics. The organizational principles developed at the Library of Alexandria continue to shape information management. Modern databases, with their schemas and relationships, echo Callimachus's Pinax. Search engines, crawling and indexing the web, follow patterns established by ancient librarians. The hierarchical organization of file systems mirrors the physical arrangement of scrolls in the library's halls. Even the concept of metadata, data about data, was pioneered by Greek catalogers. Greek cryptographic innovations remain relevant in our age of digital communication. The separation of algorithm and key, first demonstrated by the Iterative, is fundamental to modern cryptography. The layered transformations of the Polybius square appear in every block cipher. The challenge of key distribution that Greeks face with physical rods we still face with digital keys. The principles haven't changed. Only the implementation has evolved from wood and leather to silicon and electrons. The philosophical questions raised by Greek thinkers continue to challenge us. What is knowledge? How do we reason? Can machines think? What is the nature of information? These questions, first posed in ancient Athens, remain central to artificial intelligence, cognitive science, and information theory. When modern researchers work on machine consciousness or artificial general intelligence, they are grappling with problems Aristotle and Plato identified. The Greek tradition of open intellectual inquiry created the culture that makes technological progress possible. The Academy, the Lyceum, and the Library of Alexandria were spaces where ideas could be freely exchanged, debated, and refined. This tradition of academic freedom, peer review, and collaborative research continues in modern universities and research institutions. The open source software movement, where programmers freely share and improve code, follows the Greek model of knowledge as a public good. Looking forward, Greek computational ideas continue to inspire new developments. Quantum computing, with its superposition of states, echoes Greek philosophical discussions about potential and actuality. Machine learning, with its pattern recognition and generalization, implements Greek ideas about induction and categorization. Even blockchain technology, with its distributed consensus mechanisms, reflects Greek democratic principles applied to information validation. The aesthetic dimension of Greek thought also influences modern computing. The Greek pursuit of elegance, simplicity, and beauty appears in algorithm design, user interface creation, and system architecture. When programmers speak of beautiful code or elegant solutions, they're expressing Greek values. The principle that the best solution is often the simplest, Occam's razor, has Greek roots and guides modern software development. As we prepare to close our eyes and drift into sleep, let's carry with us the wonder of this continuity. The thoughts of ancient Greeks, preserved through millennia, processed by countless minds, refined by generations of thinkers, now run through billions of devices worldwide. Every computation performed, every algorithm executed, every bit of information processed connects us to those ancient pioneers who first imagined that the world could be understood through logic, number, and systematic thought. The Greeks showed us that computation is not about technology, but about thinking. They demonstrated that algorithms are eternal, independent of the medium that implements them. They proved that information can be organized, transformed, and preserved across centuries. They established that logical reasoning can unlock nature's secrets. Most importantly, they showed us that human curiosity and creativity, applied systematically to problems, can produce insights that transcend their time and place. Tonight, as sleep approaches, imagine yourself in ancient Athens, walking with Aristotle through the Lyceum, discussing logic and categorization. Picture yourself in Alexandria, watching Euclid trace his algorithm in the sand. See yourself in Syracuse, observing Archimedes refine his approximations. Feel the connection across time, the same questions, the same wonder, the same joy of discovery that motivated them motivates us still. The story of computer science in ancient Greece reminds us that we are part of a grand tradition, inheritors of intellectual treasures accumulated over millennia. The algorithms we use, the logical principles we apply, the mathematical foundations we build upon, all connect us to those ancient thinkers who first dared to imagine that the world could be understood, measured, and computed. As you drift off to sleep, remember that the computational principles discovered by the ancient Greeks continue their work while you rest. In server farms around the world, Euclid's algorithm secures communications. In scientific computers, Archimedes' methods solve differential equations. In databases, organizational principles from Alexandria manage humanity's information. The ancient Greek vision of a logical, computable universe has become our reality. Sweet dreams, and may your sleep be as peaceful as the eternal truths the Greeks discovered. Truths that continue to shape our world, one computation at a time.